Chapter 6, Air. In this chapter, we will be looking at the nature and the property of gases, then introduce you about the gas laws. Our bodies are surrounded by gases at all times. Clean, dry air is colorless and odorless. It contains about 21% oxygen, 78% nitrogen, and a small amount of other benign gaseous atoms and molecules. Of the three phases of matter, gases may be the simplest. They are simple because, unlike liquids and solids, they tend to be completely homogeneous, except under special circumstances. Gases mix thoroughly with one another. Gases are also simple because individual atoms or molecules within a gas typically do not interact with one another. Sure, they collide with one another now and then, but for the purposes of our discussion in this chapter, we can assume that the atoms or molecules of a gas do not change when they collide. In other words, they do not undergo chemical reactions. This means it is safe to assume that all of the atoms or molecules in a gas act the same way no matter what elements they contain. For this reason, we can think of any of the atoms or molecules of a gas as a generic particle of a gas. These gas particles behave like tiny billiard balls that collide and bounce. Although gases are homogeneous, and particles of a gas do not interact with one another, gases are high maintenance. One important difference between liquids, solids, and gases is how they must be stored. We can leave a sample of most solids and liquids sitting out in the open and not worry about losing any of it. That's because within solids and liquids, there are forces that hold together individual units. With gases, though, the forces of attraction are not strong enough to keep the individual gas molecules together. That is why we store most gases in airtight containers to prevent leakage. Sometimes gas leaks can be very dangerous. All gas particles move incredibly fast. A typical nitrogen molecule at room temperature moves nearly as fast as a jet plane. If we could point a radar gun at the individual molecule in a sample of pure nitrogen, however, we would find that they are not all moving at the same speed. The below graph shows the speed of all molecules in a sample of nitrogen gas at 27 degrees Celsius. The average speed of all molecules would be somewhere near the middle of the curve. Most of the molecules in the sample are moving at or near the average speed, but there are outliers that move either much faster or much slower. Gas molecules are also very far apart and take up only a small percentage of the total space of the container holding them, even though it is inevitable for them to come into contact with one another occasionally. The collisions that occur in a gas are assumed to be completely elastic, meaning that the gas molecules simply bounce off each other. We can think of the molecules in a gas as tiny, high-speed billiard balls that are in continuous random motion through space. Gas molecules move into every space available and completely fill any containers they occupy. Imagine we introduce a new gas molecule to a population of gas molecules speeding around in a container. The new molecule swiftly becomes integrated and assimilated into the existing mixture of fast-moving molecules. This process is known as diffusion. As described in the introduction section of this chapter, the canister of sarin gas used in the Tokyo subway released poisonous gas into the air. Evidence gathered after the attack showed that people closest to the canister had the most severe symptoms of nerve gas poisoning. This finding is reasonable because as the poison gas molecules moved farther from a canister, they became farther apart from one another as they diffused into the air and became diluted. A passenger farther from a canister therefore inhaled air containing fewer serine molecules, and a passenger closer to the canister inhaled more. The closer passenger would reach the fatal limits of serine with fewer breaths. Suppose that we begin with 3 identical uninflated balloons. If we take the first uninflated balloon and tie off the end of it, the balloon contains only the air that was in the room before we tied it. Next, we take the second uninflated balloon and blow 2 deep breaths into it and tie it off. Finally, we take the third uninflated balloon and blow into it until we think it might pop. Imagine that this process takes 4 breaths. Our 3 balloons looks very different now. What makes these 3 balloons different? They are different because they are all contain different amount of gas. The first balloon contains the fewest gas molecules, and the third balloon contains the most gas particles. And then the second balloon contains some intermediate number of particles. How do gas particles cause a balloon to inflate? Gas particles collide with inside of the balloon and push on it, causing it to inflate. The more particles they are, the harder they push and the larger the balloon becomes. Pressure is defined as a measure of the force applied over a unit area. In the inflated balloon scenario, the pressure is caused by the collisions between the gas particles and the interior wall of the balloon. As shown in the picture to your left, the balloon is inflated because the gas particles within it push against the inside walls whenever particles collide with them. The pressure inside the balloon pushes against the pressure of the atmosphere on the outside of the balloon. In this picture, the top tire has fewer gas particles. There are fewer collisions with the inside walls of the tire. The pressure is lower than the bottom tire. On the other hand, the bottom tire has much more gas particles. There are more collisions with the inside of the tire. Therefore, the pressure is higher. Atmospheric pressure changes with altitude. To understand why, we must know 2 things. 1. Gravity pulls everything downward towards Earth's surface. And 2. Atoms and molecules of gases are not exempt from the pull of gravity. The atoms and molecules in air are pulled downward just like everything else. So we can imagine that at sea level, the molecules in air are relatively close together because a given volume contains more of them than that same volume does in the mountains of Colorado. In other words, the air density decreases with increasing altitude. Imagine you live at sea level, say in San Francisco. After deciding to take a skiing vacation in the Colorado Rockies, you pack your bags and hop on an airplane. When you arrive in Colorado and unpack your bags, you notice that your plastic shampoo bottle is bigger than it was when you packed it back home at sea level. What's going on there? Remember that the pressure at a high altitude is less than the pressure at low altitude. The pressure inside the shampoo bottle packed in San Francisco is greater than the atmospheric pressure in Colorado. The lower atmospheric pressure in Colorado causes the shampoo container filled at the sea level to expand and push outward. One way to imagine the density of gas is to think about the motion of a handful of gas particles. We know that they travel at very high speeds and randomly carrying from one place to another, colliding occasionally with other gas particles and with the walls of their container. It follows that those collisions are more frequent in a high-density gas than in a low-density gas. We can quantify this difference in terms of the mean free path of a molecule, defined as the average distance the molecule travels between collisions. At the top of Mount Everest, molecules in the air are about 3 times farther apart than at the sea level. 180 nanometer versus 60 nanometer, the mean free path. Thus, a single breath of air on the summit of Mount Everest, represented by the clear box on the left of the picture, supplies the body with fewer particles of air than the same sized breath at the sea level, represented by the clear box on the right in the picture. Because about 1 in 5 air particles are oxygen molecules, this also means there are fewer molecules of oxygen on Mount Everest as compared to a lower elevation. This is why most climbers who scale Mount Everest rely on supplemental oxygen to get them to the top. Atmospheric pressure is the pressure exerted on us by air in the environment. It fluctuates constantly. How is atmospheric pressure measured? Scientists use a device called Barometer as shown on the left. The setup of this device is very simple. A glass column sits in a pool of mercury that is open to the air and therefore subject to the force of air molecules in its environment. Because pressure is defined as the force exerted over a given surface area, the higher the pressure on the surface of the mercury in the open dish, the farther up the tubes the mercury moves. The height of the mercury column in the tube, therefore proportional to the atmospheric pressure. A common unit for expressing pressure is millimeters of mercury. This is a measurement of the distance in millimeters. That's the mercury in the barometer tubes travels as a result of atmospheric pressure. Here are some common units of pressure. The first one is PSI, pounds per square inch. It is commonly used in measuring tire pressure in the US. The next one is the millimeters of mercury that we use in barometers. And the last one is ATM, called atmosphere. It is used in scientific measurements. And it's also given that 1 ATM is equal to 760 millimeters of mercury. Before we talk about different variables that affect gases, we have to define moles. 1 mole is 6.02 times 10 to the 23 objects. If we have 1 mole of anything, then we have 6.02 times 10 to the 23 of those things. Rather than saying this box contains 6.02 times 10 to the 23 particles of gas, we can simply say this box contains 1 mole of gas. A mole is a counting unit that makes it easy to talk about the number of particles in a quantity of substance. It is like the word dozen, which is an alternate way of talking about 12 things, like eggs or oranges. Likewise, we can use the moles to count anything. We can have a mole of eggs or oranges as well. Although moles can be used to count anything, it makes sense that we typically use the word moles when we are talking about atoms or molecules or other very tiny things. The number 6.02 times 10 to the 23 is also known as the Avogadro's number. The characteristics of gases change dramatically with temperature and pressure. Therefore, chemists have to define a standard temperature and pressure, aka STP, condition when working with gases. The temperature at STP is defined as 273 Kelvin or 0 degrees Celsius. The conversion between Kelvin and Celsius is given as K equal to degrees Celsius plus 273. The STP pressure is defined as 1 atmosphere. Regardless of what kind of gas particle, 1 mole of gas at STP fills 22.4 liters of space. There are 4 variables that dictate the behavior of a gas. They are temperature, pressure, volume, and the number of moles of gas in the sample. Changing one variable will cause one or more of the other variables to change. Let's take a look at them one by one. Gas laws are formal statements about the way gases behave. They describe the relationship between 2 of the 4 gas variables, while the other 2 remains constant. Although we call these statements gas laws, they are really nothing more than formal statements of common sense observations about the way gases behave. Your intuition about the fundamental behavior of gases is enough to remind you about each of them, as you will see next. First, let's take a look at Boyle's law. Boyle's law states that if temperature and the number of moles of gas are constant, pressure increases as volume decreases, and the pressure decreases as the volume increases. Pressure and the volume are inversely proportional to each other. As shown in the picture to your right, reducing the volume of gas-filled container like a box increases the pressure of the gas. Notice that the box contains equal numbers of gas particles before and after it is compressed. The compressed box contains gas at a higher pressure because the particles collide with the walls of the box more often. As volume goes down, pressure goes up. In other words, pressure is inversely proportional to volume. Avogadro's law states that if pressure and the temperature are constant, volume increases as the number of moles of gas increases, and the volume decreases as the number of moles of gas decreases. Therefore, the volume and the number of moles of gases are proportional to each other. In the picture to your right, in a cylinder fitted with a piston, the pressure of the gas molecules determines the height of the piston and therefore the volume of the cylinder. When more gas molecules are added to the cylinder, the piston rises and the volume increases. Another example would be when you blow up a balloon, you are increasing the number of moles of gas it contains. The volume of the balloon increases. Charles' law tells us that with pressure and the number of moles of gas held constant, increasing the temperature of a gas-filled container increases the volume of the gas. Volume is directly proportional to temperature. Imagine the same cylinder fitted with a piston. When the temperature increases, the number of collisions between the gas molecules and the interior wall of the cylinder increases. The cylinder expanded. Because we are allowing the cylinder to expand and all gas molecules are confined in the cylinder, therefore the pressure and the moles of gas are held constant. And Molten's law tells us that with volume and the number of moles of gas held constant, increasing the temperature of a gas-filled container increases the pressure of the gas. Pressure is directly proportional to temperature. Imagine we have 1 mole of gas particles in a rigid and tightly sealed box at STP. The gas molecules inside the box are moving at some average speed. If we increase the temperature in the box, the average speed of gas molecules increases. This means that each molecule collides with the inside surface of the box more often than it did at STP. Because the box is rigid and cannot expand, the volume remains constant. What does change is the pressure, because the number of collisions on the inside surface of the box has increased. You may find this page useful as it summarizes all 4 gas laws covered so far. Question 1. Which statement is true about gases? A. Gas molecules are tightly packed in a regular array and move very little relative to each other. B. Gas molecules retain their own shape regardless of the shape of the container. C. Gas molecules are far apart from one another and fill all the available space in a container holding them. D. Gas molecules are close together but move relative to one another. Please pause your video here. The correct answer is C. Gas molecules are far apart from one another and fill all the available space in a container holding them. Choice A, when you have molecules are tightly packed in a regular array and they don't really move, this is a solid. Choice B, when you have molecules retain their own shape regardless of the shape of the container, this is referring to a liquid. And then choice D is just a random wrong answer we throw in there for you. So the correct answer is C. Question 2. Which term describes the process in which air pollutants move from an area of a high concentration to an area of low concentration? A. Diffusion. B. Evaporation. C. Condensation. D. Bonding. Please pause your video here. The correct answer is A. Diffusion. Please refer back to slide number 6 for definition. Evaporation is the change of state from a liquid to a gas. Condensation is change of the physical state from a gas back to liquid. Bonding is the attraction between atoms or molecules or ions that enables the formation of a chemical compound. Question 3. Which statement correctly describes the relationship between a flat bike tire and a fully inflated bike tire? A. There are fewer gas particles in the flat tire and this results in a higher pressure. B. There are fewer gas particles in a flat tire and this results in a lower pressure. C. There are more gas particles in the flat tire and this results in a lower pressure. D. There are more gas particles in the flat tires and this results in a higher pressure. Please pause your video here. The correct answer is B. There are fewer gas particles in the flat tire and this results in a lower pressure. Recall that pressure is defined as a measure of the force applied over a unit area. There are fewer gas particles in the flat tire, which results in a fewer collisions between the gas particles and the interior wall of the tire. Therefore, it has a lower pressure. Question 4. Why is it harder to breathe at higher altitudes? A. The air contains less than 21% oxygen at higher altitudes. B. The air contains more than 21% oxygen at higher altitudes. C. The air contains more molecules at a higher altitude. D. The air contains fewer molecules at higher altitudes. Please pause your video here. The correct answer is D. The air contains fewer molecules at higher altitudes. The atoms and molecules in air are pulled downward due to gravity, so that at sea level, the molecules in air are relatively close together, because a given volume contains more of them than that the same volume does in higher altitude. In other words, the air density decreases with increasing altitudes. Less density means fewer molecules. Question 5. What statement correctly explains the molar volume of gas at STP? A. The abbreviation STP refers to standard temperature and pressure. The volume of 1 mole of gas, 6.02 times 10 to the 23 gas molecules at STP is 22.4 liters. B. The abbreviation STP refers to standard thermal parameters. The volume of 1 mole of gas, 6.02 times 10 to the 23 gas molecules at STP is 22.4 liters. C. The abbreviation STP refers to standard temperature and pressure. The volume of 1 mole of gas, 6.02 times 10 to the 23 gas molecules at STP is 1 liter. D. The abbreviation STP refers to standard thermal parameters. The volume of 1 mole of gas, 6.02 times 10 to the 23 gas molecules at STP is 1.0 liter. Please pause the video here. The correct answer is A. The abbreviation STP refers to standard temperature and pressure. The volume of 1 mole of gas, 6.02 times 10 to the 23 gas molecules at STP is 22.4 liters. This is a definition question. Please refer back to slide number 19. Question 6. What principle about gas behavior is described by Boyle's law? A. The volume of a gas increases as the pressure increases. B. The volume of a gas is not related to the pressure. C. The volume of a gas increases as the pressure decreases. D. The volume of a gas is directly proportional to the pressure. Please pause your video here. The correct answer is C. The volume of a gas increases as the pressure decreases. Boyle's law states that pressure and the volume are inversely proportional to each other. Therefore, as pressure increases, volume of the gas decreases, or vice versa. Question 7. A rigid container at a constant temperature contains 1.0 moles of gas. What happens to the volume and the pressure when an additional 1.0 moles of gas is added to the container? A. The volume doubles and the pressure doubles. B. The volume doubles and the pressure is reduced by a factor of 2. C. The volume does not change, but the pressure is reduced by a factor of 2. D. The volume does not change, but the pressure doubles. Please pause your video here. The correct answer is D. The volume does not change, but the pressure doubles. There are 4 variables involved in gas laws. The N is the number of moles of gas. P is the pressure, V is the volume, and T is the temperature. When reading the question, you notice it's mentioned a rigid container. A rigid container meaning the volume cannot change. Therefore, I'm crossing out the V term. And it says at a constant temperature. Therefore, temperature is not change. So it's crossed out. You left it with the moles. You began with 1 mole, and then you added another mole. So the number of moles doubled 2 times. Therefore, when you double the number of moles, there are more collisions between the molecules and the interior wall of the container. Therefore, the pressure doubled as well. Question 8. Which gas variables are inversely proportional to each other? A. Volume and temperature. B. Pressure and volume. C. Moles and volume. D. Temperature and pressure. Please pause your video here. The correct answer is B. Pressure and volume. Boyle's law states that pressure and volume are inversely proportional to each other. Question 9. Which change correctly explains what happens to the mean free path of a gas molecule? A. As the volume decreases, the mean free path increases. B. As the volume increases, the mean free path decreases. C. As the temperature increases, the mean free path increases. D. As the temperature increases, the mean free path decreases. Please pause your video here. The correct answer is D. As the temperature increases, the mean free path decreases. The mean free path of a molecule is defined as the average distance molecule travels between collisions. As the temperature increases, gas molecules move at a faster speed, and the chance of one gas molecule colliding with another gas molecule increases. Therefore, the mean free path is shortened. Why choices A and B are wrong? Imagine you have 1,000 gas molecules in the container. If container volume decreases, the gas molecule will have a higher chance to bump into one another. Therefore, the mean free path decreases. Question 10. What does a barometer measure? A. Pressure. B. Volume. C. Temperature. D. Moles. Please pause your video here. The correct answer is A. Pressure. Barometer is an instrument measuring atmospheric pressure, used especially in forecasting the weather and determining altitude.